Hello everyone, try this review problem as we wait for people to join. Or actually I think everybody's here, so we'll start. Or no. Okay, I think most people who had left earlier had a chance to rejoin now, so we'll start. How many subsets of two elements can be removed from the set 1 through 11 so that the mean or average of the remaining numbers is 6? So here's the formula that you might want to know that it's going to be useful in this case. So basically the formula is that 1 plus 2 plus 3 plus 4 plus ... all the way till n is equal to n times n plus 1 divided by 2. For example, we have that 1 plus 2 plus 3 plus 4 equal to, well, n is 4, so 4 times 5, or 4 plus 1, divided by 2, which is equal to 10. So here's the formula that we're going to use in this problem. So how many subsets can be removed so the average remaining is 6? Well, first let's calculate the sum of the numbers currently. The sum of the numbers, so the sum of all 11 numbers is going to be 11 times 12 divided by 2. And this sum is 66. And we want to have 9 elements remaining. We want to have 9 elements, and they have to have an average of 6. So we want to leave elements of the sum of 54. So we want 2 elements to sum to 12. So how many ways can we do this? Well, we could have 1 and 11, we can have 2 and 10, 3 and 9, 4 and 8, 5 and 7, and that's it. And if you have 6 and 6, that's not allowed because we have to have subsets. So if you have 2 of the same element, it's not a subset. And similarly, if you reverse it, 7, 5, it's not a subset since a subset is unordered. So the order does not matter in a subset. So as you can see, there are only 5 possibilities. Any questions? If there are no questions, we'll move on to homework review. What is the sum of the mean, median, and mode of the numbers? 2, 3, 0, 3, 1, 4, 0, 3. So in this problem, all we really have to do is just find the mean, median, and mode. So that's all we really have to do here. So let's find the mean first. So let's first order our numbers. We see that there's 2 zeros. And there is a 1. There's only one 1. There's only 1 2. And there are 3 3s. And there is 1 4. And let's just make sure this is correct. So originally we have 1, 2, 3, 4, 5, 6, 7, 8 numbers. And now we have 1, 2, 3, 4, 5, 6, 7, 8 numbers. So we're good. So now all we have to do is we just have to find the mean, median, and mode. So as you can see, the mode is clearly 3 because there are 3 3s and no other number has 3 or more of a number. So the mode is obviously going to be 3. The median is going to be the average of the 4th and 5th number since there are 8 numbers. And the 4th number is just going to be 2. The 5th number is going to be 3. So the median is just the average of 2 and 3, or 2.5. And the mean, or average, is just going to be the average of all the numbers. So 1 plus 2. So the mean is just going to be 1 plus 2 plus 3 plus 3 plus 3 plus 4 divided by 8 numbers. And we're ignoring the 0 since they don't add anything. And we see that 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 3 is 9, 9 plus 3 is 12, and 12 plus 4 is 16. So 16 divided by 8 is 2. The mean is therefore 2. And now we can see the sum is just 2 plus 2.5 plus 3, which is 7.5. And a good strategy on these types of problems to make sure you don't make arithmetic errors is to add both ways. So you add forward, and then you can also add backwards. You can do 4 plus 3, plus 4 plus 3 is 7, 7 plus 3 is 10, 10 plus 3 is 13, 13 plus 2 is 15, 15 plus 1 is 16. So that's another good strategy just to make sure you didn't add wrong on the AMCA, since you don't want to make arithmetic errors. This is the answer. So now we'll move on to number 2. The value of 1 over 3 times 2 over 4 times 3 over 5 dot 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 98 over 100 times 99 over 101 can be written in the form m over n. This is a long expression. And where m and n are relatively prime. Find the value of m plus n. So basically what this means is that we have to convert it to a fraction in simplest form and then basically find the sum of the numerator and denominator. So let's write some more terms to get a clear idea of what's happening. 1 over 3 times 2 over 4 times 3 over 5 times 4 over 6 times 5 over 7 dot 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 times 97 over 99, 98 over 100 times 99 over 101. So if you notice here, 3's cancel, the 4's cancel, the 5's cancel, the 6 cancel, and the denominator of a fraction cancels with the numerator 2 fractions after it. And so on, so 97's will cancel, the 98's will cancel, the 99's will cancel, and we're left with just 1 times 2. We're left with 1 times 2 over 100 times 101. And we can cancel some terms. We get 1 over 50/50. So this is in simplest form. And now we just find the sum of the denominator and numerator, which is 50/51. Move on to number 3. Mr. Garcia asked the members of his health class how many days last week they exercised for at least 30 minutes. The results are summarized in the following bar graph, where the heights of the bars represent the number of students. What was the mean number of days of exercise last week? Rounded to the nearest 100, reported by the students in Mr. Garcia's class. So we can see that there's 1 1, 3 2s, 2 3s, 6 4s, 8 5s, 3 6s, and 2 7s. So therefore, the mean is just 1 times 1, plus, since there's 1, it's 1 times 1, since there's 1 1, plus 2 times 3 of them, plus 3 times 2 of them, plus 4 times 6 of them, plus 5 times 8 of them, plus 6, and there's 3 people who have 6, plus 7 times 2, and this is equal to, and again you'll divide it by the total number of people afterwards, so 1 times 1 is 1, 6, 2 times 3, and I'll line them up so to make it more clear. So plus 6, plus 3 times 2 is 6, plus 4 times 6 is 24, plus 5 times 8 is 40, plus 6 times 3 is 18, plus 7 times 2 is 14. And this gives us, and again, the same trick, not make sure addition mistakes, is to add both ways, forward and backward. So 1 plus 6 is 7, 7 plus 6 is 13, 13 plus 24 is 37, 37 plus 40 is 87, 87 plus 18 is equal to 105, and 87, so we have the sum is 13 till here, 37 till, and then after 37, we get that's 87, and then we add 18, so if we add 18, we get value of 187 plus 18 is equal to 105, and 105 plus 14 is 119. And let's just double check and add the other way. So let's just add the other way just to make sure it's correct. So 18 plus 14 is 32, 32 plus 40 is 72, 72 plus 24 is 96, 96 plus 13 is 109, so it's 109. So that's why it's good to double check both ways, just to make sure you didn't make an addition mistake. So 109 is the total sum, divided by the number of people, which is 1 plus 3 plus 2 plus 6 plus 8 plus 3 plus 2. So 1 plus 3 is 4. 1 plus 3 plus 2 plus 6 plus 8 plus 3 plus 2, which is equal to 109 over 1 plus 3 plus 2 is 6 plus 6 is 12. And then we can just add them up and we get 25. And we can again double check our work by adding the other way. This gives us a value of 4.36. Move on to number 4. Find the value of this expression, 100 minus 98 plus 96 minus 94 plus 92 minus 90, so on. So here's how. So we can see that there are 50 numbers, because all the even numbers essentially. And we see that they're grouping them in pairs of 2. So it's just going to be 100 minus 98 plus 96 minus 94 plus dot 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 plus 4 minus 2. And there's 50 of the 50 total numbers. And since there's 50 total numbers and we're grouping them into pairs of 2, there's going to be 25 pairs of numbers. So the sum is just going to be 2 times 25 and 50, which is equal to 50. Number 5, now we'll move on to number 5. Number 5 is just to find the product of 3 over 2 times 4 over 3, so on. And all you have to do for this problem is you cancel the 3's, cancel the 4's, cancel the 5's, cancel the 2005's, and you're left with 2006 divided by 2, which is 1003. Now we'll move on to number 6. 4 students take an exam. 3 of their scores are 70, 80, and 90. If the average of their 4 scores is 70, then what is the remaining score? So here's how you do it. Let's first find, so we have 4 students, and you missed number 4, so I'll just briefly summarize it. So for number 4, you basically just grouped it into 50 groups, and then you found, okay, there's 50 total numbers, and you group them into groups of 2, and each of these 25 groups has a value of 2, so the sum is just 50. And if you want more details, you can rewatch the video after class. So that's essentially the main idea for that problem. So if you want more details, you can just quickly review the video. So there's 4 students and their average is 70. So the sum is just going to be 70 times 4, or 280. So the sum is 280, and 3 of the students are 70, 80, and 90. So we can subtract it off. 280 minus, this is going to be 240, which gives 40. So the final remaining score is just going to be 40. So are there any questions on any of the homework problems before I move on? No questions, we'll move on to today's topic, which is going to be geometry. So we'll start off with some basic formulas. So one of the most fundamental geometry theorems is Pythagorean Theorem. And Pythagorean Theorem basically says that if you have a right triangle with sides of A, B, and C, they satisfy this relation. Or a quicker way of writing this is just that we have C equal to the square root of A squared plus B squared. And as an example, let's say we have the first leg of a triangle is 3, the second leg of triangle is 4, and we're asked to find the hypotenuse. And if you aren't familiar with this terminology, the legs are basically the 2 side lengths that kind of connect the 90-degree angle. So this is a 90-degree angle. So the legs are the 2 side lengths that are touching the 90-degree angle, and the hypotenuse is the side opposite of that. So this is the hypotenuse. So we can just apply Pythagorean Theorem. So we have that C is equal to A squared plus B squared, the square root of that. So we know A squared is just going to be 3 squared, or 9. b squared is 4 squared, or 16. So c is equal to square root of 25, or equal to 5. And another thing that can be useful to save time on the AMCA is that these are some common Pythagorean triples. So 3, 4, 5 is a common Pythagorean triple. 5, 12, 13, and 7, 24, 25. And these are actually probably even more common. This is optional and can come up, but these two are the most common. And basically what a Pythagorean triple is that the 3 5ths satisfy the Pythagorean theorem. So as we saw here, C was 5. So 3, 4, 5 satisfy the Pythagorean theorem. Same thing for 5, 12, 13, and 7, 24, 25. And also in addition, if you take the multiple of any of these, if you take the multiple of each of these side lengths, so let's say we multiply 3 by 2 and 6, 4 by 2 get 8, and 5 by 2 and you get 10. 6, 8, 10 also will satisfy the Pythagorean theorem. So that's why these are some common things to know, and they can be very useful because you don't actually have to apply the Pythagorean theorem every single time, and you can just memorize these basic triples, and then you'll know when they come up, you'll know, oh, this is a Pythagorean, there's a right triangle because it's satisfied, it's a Pythagorean triple. So that's what the Pythagorean triple is. So any questions on the Pythagorean theorem or triples? Okay, so now we'll move on to area of a triangle. The area of a triangle is just going to be equal to the base times the height divided by 2. And the quick reasoning for this is you can think of drawing a rectangle on top of it. And this is just going to be half of each, this triangle is going to be just half the whole rectangle. And again, yeah, this is also another basic formula. The area of a rectangle is just going to be base times height. So the area of a triangle comes from taking half of the area of a rectangle. And another formula that's less well known is the area of an equilateral triangle. So basically, if an equilateral triangle has a side length of 2, so S equal to 2. So all these are going to be equal, and all angles will be 60 degrees. The area of it is, there's a quick trick to doing this. It's just going to be root 3 by 4 side squared. And if S is 2, it's going to be root 3 over 4 times 2 squared, or square root of 3 is our answer for this. So any questions on the area of an equilateral triangle or area of a rectangle? Okay, so then I'll move on. And another thing that is also very useful is the area of a trapezoid. What is the value? I have a question that says, what is the value of S? S is just the side length of the triangle. So if the side length is 2, so this length is 2. So this length, let me draw that better. This length is 2. That's what S is. Okay, so now we'll move on to the area of a circle. The area of a circle is just pi r squared. The circumference is 2 pi r. And another thing is the arcs of a circle. If you take an a-degree arc, so if you take some kind of a fractional piece of the circle. Oh yeah, sorry, I think I skipped the area of a trapezoid by accident. Okay, so the area of a trapezoid, basically what you do is you average the bases. So you average these bases, and then you multiply by the height. So you average these green and blue lengths, the bases of the trapezoid, and then you multiply it by the height. So that's how you calculate the area of a trapezoid. And for circles, so the area is pi r squared, the circumference is 2 pi r, where r is radius, and something that's a little bit more, something that comes up on the AMCA often is instead of taking the whole circle, you only take some part of a circle. So let's say we have an a-degree sector. So let's say we only take a out of 360 degrees. So then it makes sense that the area is just going to be a over 360 of pi r squared. And same thing for the length of the arc. It's just going to be a fraction of the circumference. So the length of the arc is just 2 pi r, the circumference, times what fraction it cuts off, a over 360. And the area is just pi r squared times a over 360. So are there any questions on any of the area formulas that we covered before we move on into some AMCA problems? Okay, so doesn't look like there are any questions. So we'll go into some AMC 8 problems now. So let's start off then. 3 identical rectangles are put together to form rectangle ABCD, as shown in the figure below. Given that the length of the shorter side of each of the smaller rectangles is 5 feet. So a key thing to geometry is whenever you have a diagram and you get information, it's always good to label, like put the information, put everything on the diagram so you can just work with the diagram. So the shorter side of each of the small rectangles is 5. So this is 5 from here to here. So this length is 5. This length is also 5. And same thing for these lengths. This is 5. This is 5 from here to here. And so we see that these are both 5. And we're asked to find the area of the rectangle, of the whole rectangle ABC. So how can we do this? Well, we can see that the total length AC, from A to C, the total length is 10. And before I even mark it here, this length is 10 because it's just a total of these 2 segments. And we know that the opposite sides of a rectangle are going to have equal length. So this is also going to be 10 then. But then we also know that these are identical rectangles. And if they're identical rectangles, they all have the same length and same width. So if the length of one rectangle is 10, the length of all the rectangles is 10. And therefore we can see that CD from here to here is 15. And BD from here to here is 10. The whole thing. So the area is just 15 times 10, or 150. Any questions on that? Okay, so we'll move on then. So now we're going to demonstrate a strategy called breaking up area. So we have some complicated area. You break it up into areas you know how to deal with. And at the end of this class, we'll see a slightly harder example that uses the same exact technique. So this 12-sided figure has been drawn on 1 cm by 1 cm graph paper. What is the area of the figure in cm squared? So how can we do this? Let's try to break it up into some areas. We know how to solve. We know how to deal with it. So we have these areas. So how can we do this? So let's find the area of this big square. So the area of the square is just 9, since it has side length 3. So 3 times 3 is 9. And now we just find the area of each of these triangles. So each of these, let me mark in different color to make it clear. Each of these green triangles, and all 4 triangles are the same, as you can see. They have a base of 2, since they're 1 cm. The base is 2, the height is 1. So the area is 2 times 1 divided by 2, or 1. So the total area is just 9, the area of the square, plus 4 of the triangles times 1, or 13. Or another way you could have done this without even using the formulas is you might notice we can just like count the squares essentially. We could just say this 1, 2, 3, 4, 5, 6, 7, 8, 9. And then these two triangles, these 2 halves put together to form a whole. So this is 10, and then 11, 12, 13. So that's another way to solve this problem, and you get the same answer. Any questions on this problem? Okay, so we'll move on then. In the diagram below, the diameter of each of the 2 smaller circles is the radius of the larger circle. If the 2 smaller circles have a combined area of 1, what is the area of the shaded region? It's where it is. Okay, so let's draw markers in our diagram. So you might be tempted to find the radius of the circle, given that we have each of these white circles has an area of 0.5, since they're equal essentially. And you might be tempted, okay, so we have these two areas. So we might be tempted to be like 1/2 equal to pi r squared. And then we might, if you try solving it, we get some ugly expression, r is equal to, or we get some really ugly expression that r is equal to 1/square root 2 pi. And then this does work, and then you can solve for the shaded region by just multiplying by 2 and doing that. But there is absolutely no point, since there's in fact a much nicer way. You don't have to deal with square root of 1/2 pi. So now I'll show that faster way. So let's just let the radius of each of these smaller white circles be r. Then we can see that the radius of the whole circle, of the bigger circle, is just going to be 2r, since we see that we have 2 of the smaller circle radiuses, right? So now let's calculate the area of each of the white circles. The area of both the white circles is 2r squared pi. And we have the area of the big circle is 4 pi, or 2r squared pi, or 4r squared pi. So what's the area of the shaded region? It's just going to be 4r squared pi minus 2r squared pi. So this is just going to be 2r squared pi. So the area of the shaded region is 2r squared pi, this region here. Both the shaded regions combined. So both of these combined have an area of 2r squared pi. And we're given that, and we see that the area of both the white circles is also 2 squared pi. This is equal to 1. Since we have given the problem, the two smaller circles have a combined area of 1. So therefore, the area of the shaded region is also just going to be 1, because it's also 2r squared pi. So that's why instead of dealing with these messy radicals, it's much easier just to assign some variables and see what areas are going to be equal, since then we can find the ratio, and then it would be much easier rather than working your calculations with this. So are there any questions on this problem or technique? Okay, since there are no questions, we'll move on. So this is a slightly more tricky problem that we're going to do. So we're given that point D is on BC, so that ACD and ABD have equal perimeters. What's the area of ABD? So the trick to this problem is we can see approximately, let's mark it on our diagram. So the trick to any geometry problem is to see, okay, let's try marking our thing on the diagram to see what information we can make from there. So we have this point, it's going to be approximately there. We don't know exactly where it is yet, but somewhere around there. Okay, so now we have this point D, let's mark a D. And we're given that ACD, ABD, and ACD. So let me just mark with the highlighter. So this triangle, this purple triangle I'm marking, and this other triangle, this green triangle I'm marking. These two triangles are equal perimeter, so we can think about that since this has this length is 1 longer than CA. Since AB, this length over here, from here to here, is 1 longer than CA from here to here. We can see that this AD is common. AD is equal for both triangles. Both triangles have the side of AB. So that's same. So we don't really care about AD. We can see that this AB is 1 longer than CA. So that means CD, which is, let me mark it. See this thing here has to be 1 longer than BD, which is this thing here. So we can write this as x plus 1 and x. So now we have that 2x plus 1 equal to 5, right? Because x is 1 plus x. So now that means that 2x is 4, since 5 minus 1, or x is 2. So that essentially means that x is 2 and x plus 1 is 3. So now that we figured out the value, let's erase it since we don't need it anymore. So we have the value, this is going to be 2 and 3. This is 2, this is 3. So now how can we find the area of ABD? So let's first find the area of the whole shape, which is going to be 3 times 4 divided by 2 over 6. The area of the whole shape is just 6. So now there's a trick here. There's a really smart trick in this problem that we're going to use later on as well. Think of this triangle lopsided, kind of. So this lopsided triangle is also the same triangle. It's the same triangle as before, we just flipped it, kind of. 3 and 4, this is 90 degrees, this is 5. This lopsided triangle, so what is this altitude over here? What is this length? So the area of the triangle is 6. Or the area of the triangle is base times height divided by 2. The area of the triangle is also going to be this base, this green base, times this height divided by 2. So that means the area, 6, is going to be equal to 5. Let's just call this one h. 5h divided by 2. And that means that we can cross multiply 6, 12 equal to 5h. H is equal to 12 over 5. So this trick is really important, and it comes up quite often on the AMCA, where you look at the area of the triangle, you look at the area of the triangle in 2 different ways. So you can look at it at this base, you can look at it as CA times AB, or you can also look at it as the altitude, H, times the hypotenuse of the triangle, which has a number 5. So make sure you understand this trick, as it's really interesting and comes up very often on the AMCA. So this H is going to be 12 over 5. Then, so now we have that. Let's draw another diagram. This length is going to be 12 over 5. So the area of ABD, this area ABD, is going to have area of the base times height divided by 2. This height is 12 over 5, as you found earlier. So the area is just going to be 2 times 12 over 5 divided by 2. So now that we find the area of ABD, it's just going to be essentially 2 times the height. We're just going to be 2 times 12 over 5 divided by 2, which is going to be equal to 12 over 5. This is a very tricky problem, so don't feel free to ask any questions. This was a very tricky problem. It had a nice, unique idea to this. Are there any questions? So make sure you understand this trick, as it can be really useful for the AMCA. So it doesn't look like there's many questions. So I think we're going to move on then. So this is another one of those special, very interesting problems. The non-convex quadrilateral, non-convex. So basically what it means by non-convex is it means that a convex polygon, any shape that's convex, basically means that all of its angles are less than 180. So this would be an example of a convex polygon, a triangle, because all of its angles are less than 180. And in this quadrilateral is non-convex. The reason it's non-convex is because this angle is greater than 180. So that's what it means by non-convex. Don't worry too much about it. As you can clearly see, that's true from the diagram. In ABC shown below, we're given that BCD is a right angle. So BCD, this is going to be this angle, is right. AB is 12. BC is 4. And CD, I'll try to mark it in here, CD, 3. BD, so, and AD is 13, so right here. So what can we try to do here? So we don't really know what to do. We have this right angle, and typically right angles, like the only thing that we really know about right angle is Pythagorean Theorem. That's really the only fact we have. So either way, we can maybe construct a right triangle. If you form a right triangle, then we can just use the Pythagorean Theorem and see where that brings us. So let's try using the let's just see if you construct a right triangle, which you can do by drawing blank BD. So now we've constructed a right triangle. And the sign to do this, the reason that we do this is because we see that we have a right triangle. And we try to form a right triangle from it. So that's why we draw the line BD. And in general, for geometry problems, it can be helpful to draw extra lines. That can help you see, oh, this has to be this area. Or it can give you some clues as to what you have to actually find. So now we can use the Pythagorean theorem. Square root of 3 squared plus 4 squared, which is the square root. Or actually, before we even use Pythagorean theorem, you can do Pythagorean theorem and get 5. Or you can just remember from earlier that 3, 4, 5 is a Pythagorean triplet. So now we know that BD is 5. So this solution, if you forget the Pythagorean triplets by any chance, it's okay, not that big of a deal. Just use the Pythagorean theorem. But a quicker way, since time in the AMC is crucial, is to just remember 3, 4, 5 is a Pythagorean triplet. So be on the lookout for those kinds of signs. So now what? Now we see that we have 5, 12, and 13. And if you remember from earlier, that 5, 12, 13 is also a Pythagorean triplet. And what does that mean? Well, that means that this is a right angle. That means that's a right angle. And that gives us a lot to work with. That means we know that means the area of ABT, the big triangle here, is just going to be 5 times 12 divided by 2, which is equal to 5 times 6, which is 30. The area of the big thing is 30, and now all we have to do is subtract off this area of BCD over here. And the area of that is pretty easy to calculate as well. It's just 3 times 4. Oops. 3 times 4 divided by 2, which is equal to 6. So the area of the quadrilateral is just 30 minus 6. It's 24. So any questions on this problem? Again, this is like a really unique trick. So extending lines, adding new lines, as you see even next week, this is like a very common and useful strategy on the AMCA. Or even other competitions too. So any questions? And this is a tricky problem, another slightly tricky problem. Okay, so let's continue. Okay, so this is okay, yeah, were there any questions on this problem before we moved on? Yeah, and this is a very unique problem because you have to extend this island, and that was a cool trick here. Okay, so I don't think there are any questions. So we're going to move on to this problem here. Point O is the center of a regular octagon ABC, DEF, GH, and X is the midpoint of side AB. What fraction of the area of the octagon is shaded? So I'm going to give you some time to work on this problem. And the hint here is to break up the areas. Break it up into areas that you know how to deal with. So that's the hint to this problem. So try solving it. So I'm breaking up into the areas now. Okay, so here's how you solve this problem. So it looks like that some of you got it, and good job. Good job to, yeah, so some of you got it, so good job to who all got it. And now I'll explain the solution to this problem. So we can break it up into eight pieces, this big octagon. So each of these octagons has its own area. So let's just assume the area of each of these triangles, each of these 1/8 triangles of the octagon be x. This will be x then. This will also be x. These are all going to be the same because they have the same base. Since it's a regular octagon, all the side lengths are going to be equal, and also the height is going to be the same by symmetry, like symmetric shape. So all these areas are all x, all of them. This whole thing is also x. And you can see that BXO, this half triangle part here, has an area of x by 2 because it's the base is half of the total triangle. So therefore, the area of the shaded region is going to be 3.5x, since there are 3.5 parts of x, divided by the total 8x, since there are 8 total triangles. This is just going to be the x cancels, so the x's will cancel, and then you'll be left with just 3.5 divided by 8, or 7/16. Any questions on this problem? Okay, so it doesn't look like there are any questions yet, so we'll move on. Quadrilateral ABC is a trapezoid. AD is 15, AD is 15, AB is 50, and BC is 20. And we're lucky they already marked it on the diagram for us. And the altitude, which they also marked, is 12. And what is the area of this trapezoid here? So here's how to get started. The altitude is going to be the same across the whole trapezoid. This will be 12. This will also be 12. So now the trick here, if you know that the altitude always makes a 90-degree angle with the base, no matter where it is. They're all the same altitude. And we can try using the area formula of the trapezoid. So try to solve this problem for some time, and I'll get back when some of you have solved it. Okay, so here's another hint. Right angles typically means Pythagorean theorem or Pythagorean triples. Oh, okay, it looks like some of you got it now. So here's the solution to this problem. As you can see, I wrote down the Pythagorean triples. You know 3, 4, 5 is a Pythagorean triple. And you can multiply by 3 to get 9, 12, 15. So 9, 12, 15 is also a Pythagorean triple. And same thing for 12, 16, 20. So we know that this has to be 9, or 9, 12, 15. And don't worry if you didn't know the Pythagorean triples stuff. You could just do 15 squared minus 12 squared, the square root of that, if you didn't remember the Pythagorean triple. except this is just a little bit faster. So that's why I used it here. And same thing for the 12, 16, 20 triangle. This has to be 16. And again, you can just use the Pythagorean theorem if you didn't remember this. And now what? We know that this is 50. So let's break it out again. We have this rectangle in the middle is 50. So that means both lengths are going to be 52. And that means the whole base, the whole base CD, the whole base is equal to, well, we know this part is 9, plus this part is 15, 50, and so we can break it up into 3 pieces, 9 plus 50 plus 16. 9 plus 50 plus 16 to 75. And now all we have to do is we just take the average. So 75 plus 50 divided by 2 times 12. And 12, 2 cancel, gives 6, which is equal to 6 times 125. That's 750. Any questions on this problem? So let's move on. A semicircle is inscribed in an isosceles triangle with the base of 16 and a height of 15. So that the diameter is contained in the base of the triangle as shown. What's the radius of the semicircle? So let's mark it here. The rate R. So, or another thing I should have mentioned earlier is that whenever you have a circle touching a line, so let's say you have some kind of a line here, and then you draw a circle. There's a special property is that if you connect the center of the circle to the point of tangency, and the point of tangency is basically where circle touches the line. So that at this point, and it barely it kind of scrapes the line. You can think of it as as it touches it for only an infinitely small point of time. So that point is called a tangency point. And the special property of tangency points is that it always makes a 90-degree angle. And if you didn't know this fact, there's also another way you could have eyeballed this. So let me just draw the radii. So in general for the AMC, you don't really have to prove your answers are necessarily correct. So what you can do is you can assume, you can make some assumptions that, okay, this seems like, whenever you see something that's close to 90 in an AMCA, it probably is 90. So you see, this looks like 90. It looks like very close to 90. And then you can just assume it's 90, since most likely, if it's on the AMCA, if it looks like 90, it probably will be 90. But this is a real way of how you get 90, the circle tangent method. So this would be 90. And let's just call this radius R. And immediately, before we even get started, the area of the triangle is just going to be 16 times 15 divided by 2, which gives us 120. And just like earlier, if you remember the trick I was saying earlier in a previous problem, calculate the area in 2 ways. So a hint to this problem is you calculate the area of this left triangle that I drew, and calculate this left triangle, this one, and calculate the area of the right triangle as well. And then you sum them, and calculate them in a different way, and try to involve R somehow. So try to involve R somehow in your area. It's a very similar style problem. So see if you can try doing that and figuring out the answer. Again, so then we have that the area of this left triangle is going to be some base, we don't know, this question mark, times this R divided by 2. So see if you can finish the problem from here. And this is again a slightly tricky problem. And even though it's 6, we're going to continue more because there were some delays in between. And again, this is going to be 90 degrees, since it's just going to be half. And this is like another, even though it's somewhat not the right way to do a problem, whenever something looks like 90 degrees on the AMCA, it probably is 90 degrees. But that's another reason why you should always make very accurate diagrams, and make sure your diagrams are to scale, and make sure you're not just making like drawing random lines, because that might be misleading sometimes. So this is a 90-degree angle, since it's just going to be half of it. And we see that the base is 16, so this part is just going to be half the base, or 8, by symmetry. And that means that the height is 15. So now we can just use Pythagorean Theorem to find this length here. So now we can see that the hypotenuse is 17. And another thing that I should have mentioned earlier is that 8, 15, 17 is also another common Pythagorean triple. You should probably memorize. But it's okay if you didn't know this, since you could just apply the Pythagorean Theorem. The square root of 8 squared plus 15 squared, which is going to be 289. And 64 plus 225, 17. So you can figure out this by 17 by using the Pythagorean Theorem, or just remembering that this is a Pythagorean triple. I'll probably add it to the handout for next time. And now we can calculate the area in 2 ways again. The area of the left triangle is going to be 17r divided by 2. Since we can think of it lopsided again, I'm not sure how you can imagine this, but let me try drawing it. This is a little bit small, but it should be okay for now. Something like that. Think of this lopsided triangle, and you can imagine kind of flipping it and drawing the altitude. Since we know that this is 90 degrees anyway, we can essentially just draw the altitude. So that's essentially just the altitude of the triangle. I know that's a little bit small. Sorry about that. So this is r essentially. This is going to be 17. And now you can try imagining, oh, the area is just going to be 17 times r divided by 2. And the same thing, so this is going to be the left triangle is 17r by 2. Same thing for the right triangle. The total area is just going to be 2 times 17r over 2, which is just 17r. So now we have 17r equal to, remember in the beginning we found the area is 120? This means that r is 120 over 17. So that's the answer to this problem. Any questions? Yeah, if you want, you can go, but if you can just watch the recording of this later if you have to go. So now we'll move on to this. I think this is the second to last problem. So let's just say that this is R. The 2 circles pictured have the same center C. Chord 80 is tangent to the inner circle at B. AC is 10. Chord 80 has a length of 16. What is the area between the 2 circles? So 80 has a length 16. That means that 80 is 8. And this is another one of those special trick problems. AC is R. BC, let's call it little r instead of big R. So big R, little r. So we're asked to find the area between the 2 circles. So what's the area of the big outer circle? Just r, big R squared pi. The area of the inner circle is little r squared pi. So therefore, the area of the annulus, or the part in between, is this minus basically this expression here. And now we see, okay, again, we see a right angle. What do right angles always mean? They always mean use the Pythagorean Theorem. So now we have that 8. We have that the square. So let me actually write that better way. So we have that r squared equal to little r squared plus 8 squared. This means that r squared minus little r squared is equal to 8 squared. Oops, not r, 8 squared. So what does this mean? Well, this means that we see that r squared minus 8 squared is 8. We can compact this expression, r squared minus r squared times pi. And we know r squared minus r squared, I'm being a little bit unclear here. Big R squared minus little r squared is 8 squared. This means that big R squared, we have just 8 squared, 64 pi, essentially. That's our answer. So again, this is another one of those interesting problems because we didn't actually have to calculate any areas. All we have to do is write our relations in terms of variables. We have this Pythagorean theorem expression, and then we just find big R squared minus little r squared pi, which we can easily do since you know the value of big R squared minus little r squared. Any questions on this problem? Okay, so this again was another really smart problem, so I think we're going to move on. Yeah, and this is our last question. So 1 by inch square cut off from this 5-inch square. What is the area, the largest square that can fit in the remaining space? So one way is just take this part here. So that's one way. But is that maximum? No. And I'll show you. I'll hear why. Another thing you can do is you can imagine something like this. Where they're all touching the other squares. They're barely touching it. So the maximal case here is when they're touching, so you have to maximize the area. So these are the same points I did here. Yeah, I should have made that a little more clear, but this is the same point. These are all the same points. That's the maximum, and I'll explain why right now. So we can think about any other shape. Like we're gonna always have some room to kind of move and fill it up a little bit more. So the maximum area is when you squish it all in. When you squish it all in, so if you had this area, and another thing that some people might think that would work is this square here. So I think that, oh, this is probably the maximum, not the regular square. We can imagine that in order to get the maximum area of the square, we want the maximum side length essentially, right? And the maximum side length is going to be try to add the extra to the square. So if you have this midpoint square, this is actually a very common mistake on that test this year, was that some people thought that it's just going to be the area of this orange square right here. But you can imagine rotating it. You can imagine rotating it to form this blue square. So you can rotate and squish it in more. So before I move on to this problem, is it clear that everybody why the blue square is going to be the maximal area square? So you can give me a thumbs. You can put a thumbs up in the participants list. You can just, because this is something that's somewhat a little bit hard to understand. So I want to make sure you understand why necessarily the blue square is going to be the maximum square. And if you have any questions about that, you can ask why, and I'll try to explain that. So let me erase the orange square now. So can you give me a thumbs up in the participants list if you understand why blue is the maximum? Or if you don't understand why, ask the question. Or I don't think you can do thumbs up. Okay, it's fine. I think, yeah. So if you have any questions, you can ask them. Otherwise, I'll move on. So now how do you find the area of this square? This again becomes a matter of breaking up area. So the trick here is, let's take this small square. The area of this small blue square is just the area of this dark blue square plus the area of these 4 triangles. So we're given that the total side length is 5. This is 5. And these are both 1. So the middle part is 3. So now the middle part is just 3 by 3 times 3 or 9. Right? And now all you have to do is find the area of each of these 4 triangles. And the height is 1, the base is 3. So the area is just going to be 3 halves. So each of these triangles has the area of 3 over 2. So the total area is just 9 plus 4 times 3 halves, which is 9 plus 6, which is 15. And that's our answer. Any questions? If you don't have any questions, you can go for now. And again, I'll send out the homework submission form where you can submit your answers and the video for this class. If you have any questions, you can ask them, or if you don't have any questions, you can feel free to go now.